Hello! In this video, we are going to prove the following theorem. Every subgroup of a cyclic group is cyclic. And if we have a cyclic group of order n, call it group generated by A, then the order of any subgroup divides n. Moreover, for each positive divisor k of n, there is exactly one subgroup of order k, namely the group generated by a to the power of n over k. Now, this is often called the fundamental theorem of cyclic groups. And in proving this theorem, we're going to be using the following preliminary results. Given a finite cyclic group G and P is an element of G, then the order of P divides the order of G. Given a group element A with order n, and k is an integer, then the order of a to the power of k is equal to n over the GCD of n and k. And given a group element A with order n, given I and j are integers, then the group generated by a to the power of I is equal to the group generated by a to the power of j, if and only if the GCD of n and I and the GCD of n and j are equal. Okay, so now let's get into proving this theorem. Now first, we're going to prove that every subgroup of a cyclic group is cyclic. To do that, let's consider a cyclic group. We'll say that it's generated by A, and we'll say that the identity element of the group is E. Now from here, we want to show that every subgroup is also cyclic. So let's let H be an arbitrary subgroup. From here, we want to show that H is cyclic. And to show that H is cyclic, we're going to consider two possibilities. Either H is trivial or H is non-trivial. If H is trivial, then this means H consists of only the identity element. Now, if H consists of only the identity element, then H is generated by the identity element. And because H is generated by the identity element, that tells us H is cyclic. So then why are these two groups equal? Well, we know that H consists of only the identity element, but it's also true that the group generated by the identity element only consists of the identity element, because if we consider an arbitrary element of the group generated by the identity element, then it's going to be of the form e to the power of k, where k is some integer. But e to the power of any integer is equal to the identity element, so e to the power of k is equal to the identity element. So when we consider an arbitrary element of this group, it must be equal to the identity element. So the identity element is the only element of this group. So because these two groups only consist of the identity element, that's how we know they're equal. So this completes the case where H is trivial. Now let's consider the case where H is non-trivial. In other words, H is a subgroup that does not consist only of the identity element. Now, we want to show H is cyclic, and the idea to do that is to consider the following set. We consider the set S, which is the set of positive integers t, with the property that a to the power of t is an element of H. The claim is, we can show that this set is non-empty, and we know that every non-empty subset of positive integers has a smallest element. That's due to the well-ordering principle. So that will tell us S has a smallest element, and the claim is a to the power of that smallest element will be a generator of H. And that will tell us H is cyclic. So, to show that, well first, let's show that S is non-empty. And to show that S is non-empty, well first of all, since H is non-trivial, we know that H does not consist only of the identity element. So we must be able to find some element in H, which is not the identity element. I'll call that element little h. Now, since little h is an element of H, well, we know that little h belongs to the bigger group, the group generated by A. So little h must be of the form a to the power of some integer. I'll call that integer gamma. Now, since H is a subgroup, we know, given any element in H, its inverse will also belong to H. So, since little h belongs to H, we know that the inverse of little h must belong to H. Now, since H is equal to a to the power of gamma, that tells us that the inverse of H is equal to the inverse of a to the power of gamma. But by properties of exponents, we know that this is just a to the power of negative gamma. Now, since H is not equal to the identity element, that means it cannot be the case that gamma is equal to 0. Because if we instead have gamma is equal to 0, then H is equal to a to the power of 0. But a to the power of 0 is equal to the identity element. So that means H is equal to the identity element, contradicting the fact that H is not equal to the identity element. So gamma cannot be equal to 0. So then we have two possibilities. Either gamma is greater than 0 or gamma is less than 0. And we're going to show in either case, we have that S has an element in it. That guarantees S must be non-empty. So what happens if gamma is greater than 0? If gamma is greater than 0, then gamma is a positive integer. So gamma satisfies this condition. And also, we know that a to the power of gamma is equal to H, which is an element of H. So we satisfy this condition as well. This tells us gamma satisfies all the conditions to be an element of S. So now, what happens if gamma is less than 0? If gamma is less than 0, then the negative of gamma is greater than 0. So the negative of gamma is a positive integer, which means it satisfies this condition, but also we know that a to the power of negative gamma is an element of H. So it satisfies this condition as well. This tells us that negative gamma satisfies the requirements to be an element of S. And so we see in either case, whether we have gamma greater than 0 or gamma less than 0, we can find at least one element in S. So S must be non-empty. So then S is a non-empty subset of the positive integers. So by the well-ordering principle, it must have a smallest element. And let's let M be the smallest element of S. Now, since M is the smallest element of S, we know that M is an element of S. So M is a positive integer with the property that a to the power of M is an element of H. So a to the power of M is an element of H, but the claim is that a to the power of M will generate H. If we can show this, then that tells us H is cyclic. And the way we're going to show that these two guys are equal is we're going to show that H is a subset of the group generated by a to the power of M, and we're going to show that the group generated by a to the power of M is a subset of H. Now, since a to the power of M is an element of H, it follows that the group generated by a to the power of M is a subset of H. The reason why is because if we take a to the power of M and multiply it by itself over and over again, in other words, if we take a to the power of M and raise it to the power of any positive integer, then we're just multiplying a to the power of M by itself over and over again. But H is closed under the operation of the main group. So when we keep multiplying this guy by itself over and over again, we're going to still remain an element of H. Also, since H is a subgroup, we know that H contains the identity element. So a to the power of M to the power of 0 equals the identity, which we know is an element of H. Also, since H is a subgroup, we know that H is closed under inverses. So we know that the inverse of a to the power of M is an element of H. But then if we multiply the inverse of a to the power of M over and over and over again, we will still remain an element of H. In other words, when we raise a to the power of M to the power of any negative integer, then we'll still remain an element of H. So as you can see, we have that every element of the group generated by a to the power of M belongs to H. But now we want to show H is a subset of the group generated by a to the power of M. And to do that, let's consider an arbitrary element of H. I'll call it B. From here, we want to show B as an element of the group generated by a to the power of m. Now, since B is an element of H, and H is a subgroup of the group generated by A, we know that B is going to be an element of the group generated by A. So B must have the form a to the power of some integer. So we can say B is equal to a to the power of k for some integer k. Now, since we expect H to be generated by a to the power of m, this means we expect every element of H to be of the form a to the power of m to the power of some integer x, which is equal to a to the power of m times x. So we expect every element of H to have this form. So in particular, we expect a to the power of k to have this form. In other words, we expect k to be a multiple of m. And to show that, we're going to apply the division algorithm to k divided by m. If we recall, the division algorithm tells us the following. Given integers a and b, where b is greater than 0, then there exist integers q and r, such that a is equal to bq plus r, and 0 is less than or equal to r is less than b. So applying the division algorithm, we're going to take a to be k and b to be m. Well, in that case, there exist integers q and r, such that k is equal to mq plus r, and 0 is less than or equal to r is less than m. Now, since we expect k to be a multiple of m, this means we expect r, the remainder, to be equal to 0. Now, we know r is greater than or equal to 0, so let's assume for a contradiction, we have the case that r is greater than 0. So what goes wrong in this case? Well, the claim is that we can show that r belongs to S. But m is the smallest element of S, so that implies m is less than or equal to r, which contradicts the fact that r is less than m. Now, to see how r belongs to S, well, first of all, since r is greater than 0, we know that r is a positive integer, so it satisfies this requirement. But now we want to show that a to the power of r belongs to H. And to see how this happens, we'll notice, what is a to the power of r? We know that r is equal to k minus mq. And then by properties of exponentiation, we can write this as a to the power of k times a to the power of negative mq. And then by properties of exponentiation again, we can write this as a to the power of k times a to the power of m raised to the power of negative q. But notice, a to the power of k is equal to b, which is an element of H. And also, a to the power of m to the power of negative q is the form a to the power of m to the power of some integer. So this guy must be an element of the group generated by a to the power of m. But at this point, we've established that the group generated by a to the power of m is a subset of H. So this means a to the power of m to the power of negative q must be an element of H. So this tells us that both of these guys that are being multiplied are elements of H. But remember, H is closed under the operation of our group, so we know that the product of these two guys is an element of H. And this is equal to a to the power of r, so this shows that a to the power of r is an element of H. So r satisfies this requirement as well. So r satisfies all requirements to be an element of S. But since m is the smallest element of S, this means m is less than or equal to every element of S. So in particular, m is less than or equal to r. But that contradicts the fact that r is less than m. Now, our assumption that r is greater than 0 led us to a contradiction, so it can't be the case that r is greater than 0. Now, we know that r is greater than or equal to 0, but we've just eliminated the possibility that r is greater than 0, so we must have r is equal to 0. But now, since r is equal to 0, we have k is equal to mq plus 0, so k is equal to mq. So now we see that b is equal to a to the power of k, which is equal to a to the power of mq. And by properties of exponentiation, this is a to the power of m to the power of q. But remember, this is of the form a to the power of m to the some integer. So it must be an element of the group generated by a to the power of m. So this shows that b is an element of the group generated by a to the power of m. So putting this together, we have shown if b is any element of h, then b is an element of the group generated by a to the power of m. That tells us h is a subset of the group generated by a to the power of m. And now that we know h is a subset of the group generated by a to the power of m, and the group generated by a to the power of m is a subset of h, these two inclusions imply that the two groups are equal. And that tells us h is cyclic. So we started out given a cyclic group, and we considered an arbitrary subgroup of that cyclic group. On one hand, if h is trivial, well then h is immediately cyclic. On the other hand, if h is non-trivial, we've just shown that h is cyclic. And therefore, every subgroup of a cyclic group is cyclic. So this proves the first part of the theorem. Now let's prove the next part. We're going to suppose that the order of our cyclic group is n. And we want to show that the order of any subgroup divides n. So let's consider an arbitrary subgroup. I'll call it h. The whole goal is to show that the order of h divides n. Now, we've just shown that h must be cyclic. So h is generated by some element. I'll call it p. Now, of course, since p is an element of h, and h is a subgroup of the group generated by a, we have that p is an element of the group generated by a. So p is an element of this finite cyclic group. But according to star, we know that the order of p must divide the order of this group. But note, the order of p is equal to the order of the group generated by p, right? In general, for any group element G, the order of G is equal to the order of the group generated by G. And since the group generated by P is equal to H, this is the same thing as the order of H. Also, we know that the group generated by A has order n. So, substituting order of P with order of H, and substituting order of group generated by A with n, we have that the order of H divides n. So we have shown the order of any subgroup divides n, which is exactly what we wanted. So now let's move on to the next part. We want to show for each positive divisor k of n, there is exactly one subgroup of order k, and it's the group generated by a to the power of n over k. So to prove that, let's consider an arbitrary positive divisor, k of n. From here, the claim is that the group generated by a to the power of n over k is the unique subgroup which has order k. Now, first of all, clearly, this is a subgroup of the group generated by A, because these two guys are both groups under the same operation, and every element of this group belongs to the group generated by A, because every element of this group is going to be of the form a to the power of some integer. But the claim is that the order of this subgroup is equal to k, and it's the only subgroup that has this property. Now, to see how the order of this subgroup is equal to k, well, notice we have that the order of the group generated by A is equal to the order of A, and the order of the group generated by A is equal to n. So this tells us that the order of A is equal to n. And also, the order of the group generated by A to the power of n over k is equal to the order of A to the power of n over k. And now we see that we're in a position to apply star star, because we have a group element A of order n, and if we replace k with n over k, then the order of a to the power of n over k is equal to n over the GCT of n and n over k. But what is the GCD of n and n over k? It's equal to n over k. The reason why is because, in general, if we have two positive integers, a and b, and we know that b is a divisor of a, well then this implies that the greatest common divisor of a and b is equal to b. Right, so applying this result, we know that n over k divides n. So the greatest common divisor must be n over k. Then we know that n divided by n over k is just equal to k. So this shows that the order of the group generated by a to the power of n over k is equal to k. But now we want to show that the group generated by a to the power of n over k is the only subgroup which has this property. To prove that, let's consider an arbitrary subgroup which has this property. I'll call it J. Now, we know J is a subgroup of a cyclic group, so J is cyclic, which means J has some generator. And we could call that generator P. So we could say J is generated by some element, P, and we have that P is an element of J. And since J is a subgroup of this cyclic group, well, that implies P must be an element of that cyclic group. So we can write P in the form a to the c for some integer c. So let's just immediately say J is generated by some element a to the power of c, where c is some integer. But then notice, we have k is equal to the order of j, but we know that j is equal to the group generated by a to the power of c. So their orders must be equal. But then we know that the order of the group generated by a to the power of c is equal to the order of a to the power of c. And now we can apply star star. By star star, we know that the order of a to the power of c is equal to n over the GCD of n and c. So now, if we multiply GCD of n and c to the other side, divide k to the other side, we get that the GCD of n and c is equal to n over k. But we've just established that n over k is equal to the GCD of n and n over k. So now, we're in a position to apply star star star. Replacing I with c and replacing j with n over k, well, we know that the GCDs of these two guys are equal, so we can conclude this happens. The group generated by a to the power of c is equal to the group generated by a to the power of n over k. But the group generated by a to the power of c is equal to j. So this shows that j is equal to the group generated by a to the power of n over k. And that shows the group generated by a to the power of n over k is unique. And so this completes the proof. And so yeah, that's pretty much it for this video.